Okay, so this is general equilibrium with Kc, Kp, and Le Chat's principle. So as many of us know, many reactions do not completely finish, but they do find a balance somewhere between the reactants and the products. So the reactants are forming the products at the same rate the products are going back into reactants. And so the reactants will decrease, products will increase in concentration until they reach their equilibrium point, at which point everything should remain in a constant concentration. And the equilibrium constant, which is known as K, is an easy way to see the ratio between the products and the reactants while a reaction is at equilibrium. And it's pretty simple to solve for. You just do you multiply the concentration of the products over the concentrations of the reactants, and then you raise each item to the power of whatever its coefficient is in the reaction. And if everything in the reaction is gaseous, then you can use partial pressures as well as concentrations. And if K is greater than 1, it means you have more products. And if K is less than 1, it means you have more reactants once you reach equilibrium. And the larger or smaller that K is, the larger this difference will be between reactants and products. So here's a little practice problem for us to do. So we have 0.1 molar NO, 0.05 molar H2, and 0.1 molar H2O. And as we can see from the reaction here, there is also nitrogen involved as a product, but none of it was present initially. And then we also get the final equilibrium concentration of NO. So if we want to find K for this reaction, the first thing we do for reference is we make our equilibrium expression. So per the formula, we have our products over our reactants, and they're all multiplied together, and they're raised to the power of their coefficient in the reaction. And then we need to make this thing called an icebox. It's pretty similar to a BDA table, except it deals with the concentration as it goes from its initial state to its equilibrium state. So we have the initial concentrations of everything in the reaction, and we also have the final concentration, or the equilibrium concentration of NO. And using the coefficients in the reaction equation, we can do this thing right here. We can use these x's as stand-ins for our unknown change. And of course, the reactants decrease while the products increase. So since we have one complete column here with NO, that's all we need to solve for it. So we basically do some pretty simple algebra. You just find the difference between the initial and the equilibrium, and then divide it by 2 to get 0.019, which is x in this case. And then using x, we can do some very simple math here to find the final concentration, or the equilibrium concentrations of all of the things in the reaction. And then it's only a small matter of plugging it into our Kc expression, and we multiply the final concentrations of the reactants and the products, square them where needed, and you would get a final number of 650 for our equilibrium constant for this reaction. So Q constant is basically the same thing as K. You solve for it the exact same way, but it's for the concentrations of a reaction at any single given point, not necessarily on equilibrium. So going back to that kind of curved graph, it would be anywhere on that curve before it reaches equilibrium point, or if it goes past equilibrium, if it over completes per se. But by comparing Q to K, we can see what a reaction is going to do after that given point. So if K is greater than Q, it means that there's more reactants than products. Or there's there's too much reactants. So the reaction will decrease reactants and increase products until they level out. And the vice versa, for if Q is greater than K, then that means there's too many products. So it decreases the products and the reactants increase a little bit until they're equal. And we want K to equal Q. If Q is already equal to K, it means it's at equilibrium. But otherwise, it will always compensate for itself to bring it to the middle. And speaking of compensating, Le Chat's principle basically states that a reaction will always adjust itself and compensate to balance out any changes that happen to it. So changes could be the addition or removal of a reactant or a product, changing the volume of the container the reaction is in, changing the temperature at which the reaction occurs. And so if you lower the volume, the reaction shifts to the side with less moles because it wants to maintain the same pressure, and vice versa. For increasing the volume, it will go to more moles so that there's more matter, or not more matter, more particles per se, that will create the same amount of pressure. And then in exothermic and endothermic reactions, with an exothermic reaction, you can think of heat as a reactant, and in endothermic, you can think of heat as a product. So if it says heat is added or heat is removed, then you can think of it like that, because think of it like this scale here. So there's reactants and products. If you take away products, then obviously the reactants would tip the scale in its favor, so you want to go to products instead. So I like to draw that on my FRQs to make sure everything as a visual reference per se. So thinking of heat as a reactant or a product it's not officially the right reasoning, so don't write it down on an FRQ, but it helps me get to the right answer. And so another way to think of it is just increasing temperature favors the endothermic direction, decreasing temperature favors the exothermic direction. And going back to the same reaction as our example problem over there, if we were to remove nitrogen, then it would shift to the right to create more products and compensate for that lack of nitrogen. And then if we were to increase the volume, the reaction would shift left because there's more moles on the left side, 4 versus 3. That would create a constant pressure so that the reaction remains in its ideal state.